Mr. Chairman, honorable guests, ladies and gentlemen, good afternoon. It's a very great pleasure indeed for me to attend this conference. Today, I'd like to present my paper, Electrical Characteristics Analysis of LSCs under Composite Fault. My presentation will cover the following aspects: introduction, method, results, and conclusion. Part 1. Introduction. Large-scale synchronous condenser (LSC) is a special type of synchronous machine without mechanical load and operating in a continuous no-load condition. LSCs are selected as a main dynamic reactive power compensation device for ultra-high voltage direct current transmission projects. Owing to the variable operation of the system, the possibility of inner faults for the machine is relatively high. To maintain the stable power transmission, the operation safety of LSC should be focused. There are two common types of faults in LSC: transducer short circuit in stator winding (TTSF) and dynamic rotor eccentricity (DE). Quantities of researches have been carried out on the single fault, but little literature explored the diagnostic criteria of their composite faults. Actually, these two faults usually happen in company. In this paper, the easily observable stator winding circular current and the reactive power outputs of LSCs are used to distinguish these two types of faults and their composite faults. The fault characteristics during the dynamic process of sudden terminal voltage changes are also taken into account. As a result, we concluded the diagnostic criteria consisting of those two characteristics to classify the fault type in different operating states. Part 2. Method. In healthy condition, because of the symmetry structure, the voltage difference between the branches is zero. Consequently, there's no circular current in the branches of stator windings. Owing to the change of air gap permits, dynamic eccentricity leads to significant even-order components in the voltage difference in the same as circular current. And there's fundamental and triple frequency components when TTSF happens. There are two types of operating modes for LSC. Depending on the excitation, they are divided into two regions. In leading phase operation, LSC absorbs inductive reactive power from the system. In other words, reactive power output is capacitive. While in lagging phase operation, LSC will output inductive reactive power to compensate the system. The formulas for calculation are shown on the slide. An FEA model was built on the basis of Table 1. The degree of eccentricity is defined as the ratio of the offset and the air gap length. The geometric center of rotor is offset by 10, 15, and 20 centimeters to produce 14%, 21%, and 28% dynamic eccentricity. Figure 6 is a circuit model in flux. The excitation current in simulation is 708 ampere, so that the LSC is working in the leading phase operation. Switch 1, 2, 3 and set to be closed to make a dynamic condition of the terminal voltage sudden change. Switch 4 is set to be closed to make the TTSF of 3 terms in one of branches of phase C. Part 3. Results. In order to simplify the description, we numbered the 8 conditions studied as is displayed in Table 2. The circular current waveforms under different degree of eccentricity are shown in Figure 7. With the degree of eccentricity increasing, the amplitude of circular current also boosts. As is depicted in Figure 8, the circular currents under composite fold are not equivalent to the sum of the other 2 cases. From the FFT spectra, we can see that when TTSF happens, the fundamental and the odd-order current components rise up apparently in both steady and dynamic states, while the prominent second harmonic also exists after a sudden terminal voltage drop. In the case of DE, the dominant contents are even order, especially the second harmonic. Meanwhile, the magnitude of all components enhance with the incremental eccentric degree. The waveforms and component spectra for reactive power output are displayed in Figure 10. It infers that once TTSF happens, the odd-order component will emerge in the capacitive reactive power outputs. Because there are apparent 6 harmonics in every case, the following index is defined to indicate the severity of the faults. The tendency of this index is shown in Figure 11. Obviously, when in healthy condition, this index is equal to 1, but when dynamic eccentricity happens, the index is lower than 1, and when TTSF happens, the index is bigger than 1, as well as composite faults. Switch 1 to 3 were said to be closed to make a sudden drop of the terminal voltage at 3 seconds. To maintain the stable power transmission of the UHVDC systems, the LSC will output inductive reactive power when there's a drop in AC bus voltage. The statistics in Figure 12 indicate that dynamic eccentricity leads to a rise on the magnitude of reactive power comparing to the normal condition. However, the value decreases while TTSF existing. In the situation of composite fault, the peak value is even lower than under TTSF. After the FFT analysis of the above waveforms, it is found that there are obvious 7th harmonics in the first period when single fault happens, while when composite fault occurs, this kind of component is disappeared. Part 4. Conclusion. Because of the existence of the same characteristic corresponding to different types of fault, the intersectional fault characteristics are more accurate to classify the fault. The intersectional fault characteristics are listed in Table 3. When considering the intersectional characteristics, it is more clear to distinguish these types of faults. The electrical characteristics of LSC under radial DE of rotor, TTSF, and their composite faults are analyzed using field circuit coupled FEA simulations in both steady and dynamic process. These faults can be distinguished by comparing the waveforms, FFT spectra, and magnitudes of circular currents in the stator winding and the reactive power outputs. That's all. Thank you for your time and attention.